This is Chapter 17, Human Health and Environmental Risks. The opening case study is about a citizen scientist named Margie Richard. Margie became a citizen scientist to help document the health risk of nearby chemical plants. This occurred in Norco, Louisiana. There are about 1,500 residents in a 4-block area close to Shell oil chemical plant and oil refinery. In 1973, a pipeline explosion blew up a house and killed 2. And in 1988, 7 were killed in a refinery accident, and that sent 70 million kilogram toxic chemicals into the air. 1/3 of the children suffered from asthma, and there was a lot of clusters of cancers in the region. In 1989, local residents and middle school teacher Margie Richard organized what was called the Bucket Brigade to collect air samples and document what Shell was releasing. They found 0.9 million kilograms of toxic chemicals were being released annually. So in 2002, Shell agreed to purchase the homes from the people in the neighborhood and pay $5 million for community development. They also agreed to reduce their air emissions from their refinery by 30%. In 2007, Shell continued with their plight. They agreed to its violation and paid the state of Louisiana $6.5 million in penalties. Margie Richard received the Goldman Environmental Award, and this honors grassroots environmentalists. She is a true citizen scientist. This chapter looks at human health and what affects human health. And there's 3 main risk factors. The categories are physical, biological, and chemical. Physical risks are environmental factors such as natural disasters, exposure to UV radiation, and accidents. Biological risks are associated with disease that impairs the function of the body with a characteristic set of symptoms. And chemical risk is associated with being exposed to chemicals that are either naturally occurring, like arsenic, or to synthetic chemicals and pesticides. The World Health Organization says that the leading causes of death in the world are caused by disease, that more than 3/4 of those deaths are diseases, including respiratory, digestive diseases, cancers, cardiovascular, and infectious diseases. Among the world's deaths caused by infectious diseases, 94% are caused by only 6 types. So if we take a look at this pie chart, we can see that cardiovascular disease is 29%, followed by infectious disease, cancers, respiratory and digestive, injuries, maternal and perinatal. Perinatal means before birth conditions, and then others. But of the infectious diseases, those are tuberculosis, malaria, childhood diseases, respiratory infections, HIV, and diarrheal diseases. So biological risks are, like I said, infectious diseases, those that are caused by infectious agents known as pathogens. Pathogens can be viruses, bacteria, fungi, protists, helminths, which are worms, and they can cause a variety of different illnesses. 3 examples would be pneumonia, stomach flu, or a rotavirus, and venereal disease. Elephantitis is caused by the bite of an infected mosquito with filarial worms. The parasites lodge into the lymphatic system of humans and cause blockages, causing this elephantitis. Biological risk can come in 2 forms. We have chronic disease and acute diseases. Chronic diseases slowly impair the functioning of a person's body. Some examples might be Parkinson's, Alzheimer's, MS, or multiple sclerosis. Acute diseases rapidly impair the function of a person's body because they have a quick onset, so they're considered acute because they're quick. Common cold, stomach virus, and appendicitis would be acute diseases. Risks differ between developing and developed countries. So think about this logically. Developing countries are very poverty-stricken, and that poverty can lead to chronic disease. 1/2 of children under 5 die from pneumonia due to poor nutrition, and 3/4 of children who die from diarrhea are malnourished. The reason that they die is because they don't have the nutrients in their body and the energy to fight infection once they develop these diseases. Why does this happen? Well, usually there's a reduced government support for agriculture in the areas, and there's higher costs of fossil fuels leading to increased food prices, and these people can't afford to buy the food because they can't afford the fossil fuel prices. So if you take a look at low-income countries versus high-income countries, you can look at the different health risks. So in a low-income country, low weight during childhood is the leading cause of death. High blood pressure among adults, unsafe sex that might lead to HIV or other sexually transmitted diseases, unsafe water, sanitation, and hygiene, which can lead to diarrheal and other abdominal diseases, high blood glucose because their diets are often rich in carbohydrates and lacking in the protein that their body needs. Indoor smoke from solid fuels because they have to burn biomass usually to heat their water and cook their meals. Many of them smoke because smoking satiates the hunger so that they don't feel hunger. Physical inactivity, so because they don't feel well, they don't get enough inactivity, and so that can lead to heart disease. And then suboptimal breastfeeding, because the women are not healthy to begin with. When they're breastfeeding, the milk that they're feeding their babies from their breasts is not high in nutrients. And then some of them have high cholesterol because we know that diets high in just carbohydrates do not lend a healthy lifestyle. And then if you look at a high-income country, tobacco use is the leading cause of death, followed by high blood pressure, overweight and obesity, physical inactivity, high blood glucose, high cholesterol, low fruit and vegetable intake, urban outdoor air pollution, alcohol use, and occupational risks. So some of the historical diseases that we want to just mention would be the plague. Yersinia pestis is the genus and species of the bacteria that's carried by fleas on rodents. And malaria, Plasmodium, is caused by a parasite in the female mosquito, and the genus is Anopheles mosquito. Tuberculosis is caused by a Mycobacterium tuberculosis, and it's spread in the air from person to person. It affects the lungs. 20% of people in Russia carry a drug-resistant strain of tuberculosis, which means that it's antibiotic resistant. An epidemic is when a pathogen causes a rapid increase in disease, and a pandemic is when an epidemic occurs over a large geographic region, such as an entire continent or the entire world, like as what's being experienced by COVID. Emergent diseases are diseases that have not previously been described or not common for at least the prior 20 to 30 years. So HIV and AIDS is a virus that spreads through sexual contact or shared needles, and this is one of the emergent diseases. Ebola hemorrhagic fever is a virus that kills within 2 weeks, where people bleed. Hemorrhagic means bleeding. And mad cow disease is also called bovine spongiform encephalitis, or BSE. It's caused by a prion, which is a protein in the brain that can mutate into deadly proteins and act as a pathogen. The human version of this is often called Creutzfeldt-Jakob disease, or CJD. Cattle that get infected with mad cow disease must consume nervous system of an infected cow. And then we have the bird flu, or avian flu, H1N1. This is a virus that in 1918 killed more than 100 million people. A form of the bird flu, H5N1, came about in 2009 where the virus jumped from birds to humans. And our bodies, because we've never seen it before, did not recognize it, and it killed 400 people, which was about 50% of the people that got infected. So consequently, thousands of birds had to be killed to prevent the spread further. The West Nile virus is a virus that's transmitted by mosquitoes. And then we have COVID-19, a coronavirus that's transmitted originally by contact with bats. A zoonosis is a zoonotic disease, or zoonoses, which is the plural of zoonosis, is an infectious disease that is transmitted between species from animals to humans, or from humans to animals. So if we look at COVID, West Nile, bird flu, these are all transmitted between, they're infectious in between animals and humans. So the different pathways of disease transmission would be other humans. We can get sick from them. We can get sick from water. We can get sick from air, food, wild animals, and domesticated animals. So let's take a look a little bit closer at some of these diseases. So HIV is a disease it's a virus that was found, early on before 2006, but in 2006, researchers found that chimps in Cameroon carried a virus similar to HIV. So what they decided was that they likely think that chimps are the source of HIV. Hunters were probably exposed to the chimps and to the virus, I should say, when they were butchering and eating the chimpanzees. And so it jumped species. Ebola hemorrhagic fever is the fever that kills people within 2 weeks. It's a virus, I meant to say. It kills other primates, so they are not likely the long-term host of the virus. And what I mean by that is a virus, if it kills the long-term host, cannot continue on. So there's usually an intermediate host, and that's not the case for Ebola. If we take a look at mad cow disease, this is interesting because this is due to a prion. Cows are fed nervous systems of other cows and sheep that are infected with harmful prions. And so before we knew this was a possibility, we didn't realize that it was the prions that was causing the problem. Humans who consume the beef can become infected as well and develop what's called Creutzfeldt-Jakob disease, where the neurologic system is drastically impaired. Prions are small beneficial proteins that sometimes mutate to be harmful. What's really interesting about mad cow disease is that there's a disease that's very similar called Kuru. It's very rare, very rare. It's caused by an infectious protein or prion found in contaminated human brain tissue. Kuru is found among people of Papua New Guinea who practice a form of cannibalism in which they actually eat the brains of dead people as part of a funeral ritual. And they're still tracing this and trying to see if people are still suffering, and they are still in certain areas of Papua New Guinea. Bird flu, or H1N1, which is the normal form of bird flu, normally infects birds, but in 2006, a related form of H5N1 jumped from birds into humans and killed about 400 people. Like I said earlier, about 50% died. What happens is wild birds, which do not become ill, pass this on to domesticated birds, like these chickens in this chicken coop. And the problem is that the workers are in there working with them and handling the birds, whether they're feeding them, watering them, cleaning up after them, or butchering them. And when they do this, they're exposed to the virus that was passed from the wild birds to the domesticated birds. West Nile virus is a virus that lives in birds and is transmitted among birds by mosquitoes. It causes human infections and deaths. It also can be transmitted easily in horses. In fact, a horse in my neighborhood was killed by West Nile virus. What's interesting about West Nile is that there were virtually not very many cases. And then in the early 2000s, we had this significant jump in infections, and we had significant jump in deaths from West Nile. And then they've kind of come down. We know how to treat it. The thing about West Nile is if you become infected by it, you can have long-term health effects from it. You can recover from it, but some people have long-term health effects. There are also chemical risks to human health. Some of these are neurotoxins, which disrupt the nervous system. Some examples might be lead and mercury. Carcinogens are cancer-causing agents, and what these do is cause mutations. They're also called mutagens, and they damage genetic material, and then those damaged cells reproduce inside the body and can cause tumors. Teratogens are chemicals that interfere with the normal development of embryos or fetuses. An example is thalidomide that was used for morning sickness, and it caused deformities in developing fetuses. Allergens are caused by allergic reactions when the immune system has an abnormal response to something that it comes in contact with. Endocrine disruptors are chemicals that interfere with the normal functioning of hormones in an animal's body or a human's body. So teratogens, let's take a look at this. Thalidomide, like I said, is a medicine that was used in the 1950s and 60s to treat morning sickness. The result of that was that it caused severe birth defects where children were born with shortened limbs or missing limbs and missing fingers. And you can see these children all are their upper arms and extremities are greatly impaired. Sometimes they don't even have the same number of fingers and toes that we would normally have. An endocrine disruptor is a chemical that interferes with normal hormonal functioning in the body. Fish and amphibians are uniquely susceptible to this because they live in water, and some of these endocrine disruptors are easily moved into watersheds. So what happens is that the fish and amphibians become effeminized when exposed to these human hormones, and it could be from birth control pills or hormones that are given to animals and CAFOs. Certain pesticides as well, like atrazine, can act as an endocrine disruptor. So let's take a look at what happens. On the left here, you'll see what normally happens. A hormone attaches to a receptor molecule right here. So the green is the hormone and the blue is the receptor molecule. And that triggers a response in the animal. So normally estrogen is converted to testosterone and male features develop normally. So that's what happens when in a male fish or amphibian and even humans. But what happens if there's an endocrine disruptor in the body is that it attaches where the hormone would normally attach, blocking the response of the hormone and the receptor molecule. Consequently, there's no response, so that estrogen is not converted into testosterone, and that makes the males have low sperm counts and also develop eggs in their testes. Some chemicals of major concern that we need to be aware of is lead, that's found in paint and gasoline. It's a neurotoxin and it can impair learning in the nervous system. Mercury, which is from coal burning power plants and consuming fish that are exposed to this. It's a neurotoxin, and by the way, remember that mercury can biomagnify up the food chain. It can damage the brain, kidneys, liver, and the immune system. Arsenic is a naturally occurring element found in mining and groundwater. It's carcinogenic or a cancer-causing agent. Asbestos is found in building materials. It's also carcinogenic, and it can also impair breathing and lead to a specific cancer called mesothelioma. PCBs, or polychlorinated biphenyls, are found in industry. They're carcinogenic and also can lead to cancer, impaired learning, and liver damage. Radon, which is naturally occurring and found in soil and water, is carcinogenic, can lead to lung cancer. Vinyl chloride from industry, it's found in vinyl chloride pipes as well. It's a carcinogen and a cancer-causing agent. Alcohol is a teratogen, so we find alcohol in alcoholic beverages, and this can impair the growth of fetuses and reduce fetal brain development and nervous system and cause nervous system damage. Atrazine, as I just mentioned before, is a herbicide that's also an endocrine disruptor that can feminize the male species of amphibians, fish, and humans. DDT as well as an endocrine disruptor. It's an insecticide. And then phthalates, which are found in plastics and cosmetics. They are also endocrine disruptors and can feminize males. So what is a dose response study? So dose response is when we look at the lethal dose or the effective dose. Lethal dose is a dose that kills 50% of individuals. The LD50 or the ED50 values are divided by 10 to determine safe concentrations for rats and mice. The LD50 for humans is divided by 1,000 to ensure extra caution. And ED50 or effective dose is the dose that causes 50% of the animals to display a harmful effect, but not a lethal effect. So ED50, the animals don't die, but LD50, 50% of the animals do die. So this is how we determine the safety of different chemicals. It could be also medications we take. For example, if you are given a new medication for some disorder or to treat something like maybe anxiety or something, they have done an LD50 on that medication to find out, okay, well, at what point do 50% of the individuals die? So they will take that value and divide it by 10 to determine safe concentrations for rats and expose them to that again and see if they are right, that only 50% die when exposed to that amount. If more die, then they'll have to adjust their values. Then once they get the LD50 for rats and mice, then they divide that number by 1,000 to make sure that it's safe for human consumption. That's how we determine safe doses for medications and chemicals. So if we look at this in a graph, an LD50 study is used to determine the dose of a chemical that causes 50% of death rate. Scientists exposing animals to different doses of a chemical and then determine what proportion of those die at each dose. So for example, if we look at percent of mortality, so this is where 0 would die, and this would be where 100% die. And we look at a hypothetical chemical that we're exposing animals to, mice and rats. At dose 2, 4, and 6, you can see what happens to this line. 50% right here, 50% would cross this intersection right here. So the LD50 for this particular chemical would be not quite, it would be greater than 5, but not quite 6. So it's like 5.5, right in the middle there, because 5 would be right here about, and that would be halfway between 5 and 6. So I would suggest that that would be 5.5. So that's how you determine the LD50 when you're given the data from a dose response study. Epidemiology is a field of study to understand what causes illnesses and diseases in humans and wildlife populations. A retrospective study is a study that monitors people who have been exposed to a chemical in the past, and a prospective study is a study that monitors people who might become exposed to chemicals in the future. For example, people who are tobacco and alcohol users could be part of a prospective study to see how the long-term effects have affected them over their lifetime. Synergistic interactions are when two risks come together and cause more harm than one would. A great example of this is the health impact of a carcinogen such as asbestos, and that impact could be much higher if the individual also smoked at the same time that they were exposed to the asbestos. In 1984, there was a massive release of methyl isocyanate gas that killed and injured thousands of survivors of a chemical disaster in Bhopal, India. So they've done a retrospective study to find out how the survivors are doing long term and what the health effects have been for them after the chemical exposure. And what they found, if you can take a look at this chart, is that those that were exposed experienced high levels of respiratory symptoms. Those that were not exposed did not. And of those that were exposed, they experienced higher levels of stillbirths than those that were not exposed. So these are people in Bhopal, India that experienced this release of methyl isocyanate gas. So some routes of chemical exposure for humans could be, we get it from the air, if it's air pollution, water. Our babies can get it because it can directly be infiltrate cord blood and then directly go into the fetus itself. And then also breast milk. And then soil, we can get it in our soil. And then the food that we eat. If the food that we eat has toxins like pesticides and herbicides, in the soil, those pesticides and herbicides don't necessarily disappear either. Some of them can persist for a long time. And we've talked about water pollution and air pollution at length. Bioaccumulation is when there's an increased concentration of a chemical within an organism over time. So this is bioaccumulation. As the chemical accumulates over time in the fatty tissues of the organism, the chemical becomes more concentrated. So you can see, as a fish is small and just developing, it might be exposed to a chemical, but as it grows and exposed to that same chemical over and over and over, eventually its accumulation is much greater. Biomagnification, on the other hand, is different. This is an increase of a chemical in concentration in the animal tissues as the chemical moves up the food chain. So if you take a look at this, the DDT might be sprayed into an aquatic ecosystem at 0.00005 parts per million. And then it's absorbed or taken in by the zooplankton or the phytoplankton. But then look at how much it's increased. That concentration is now 0.04 parts per million. Then maybe this little stickleback feeds on some of that plankton, and now that mercury is magnified and is 0.26 parts per million, and then it's eaten by a flounder. Now it's 1.28 parts per million, and then that flounder is eaten by an osprey, and look at how much greater the mercury content is now in the osprey. It's 13.8 parts per million when it started out being sprayed into the water at only 0.00005 parts per million. So this is a big problem, and this is what happened to the bald eagles in the 70s. So during the 50s and 60s, we were spraying DDT like crazy into bodies of water to kill mosquitoes, and it biomagnified up the food chain. And because the bald eagles were, fishers, they eat a lot of fish, they were getting high levels of DDT in their bodies. And when they would try to reproduce, the shells of the eggs would either not develop or they would be so brittle that the babies couldn't develop in the shell. Another example is the mercury in dolphins and fish. And so, we've talked about this, that the mercury in especially the dolphins on the near Asia, because there's so many coal-fired power plants and the mercury falls into the ocean as particulate matter, it biomagnifies up the food chain in the dolphins and the fish as well there. So just a comparison between bioaccumulation and biomagnification. So bioaccumulation is what occurs over time in a species, where biomagnification occurs in a food chain and increases in concentration up the food chain. So persistence refers to how long a chemical can remain in an environment. Some chemicals are broken down by light and water and microbes really quickly, while others remain. And if you take a look at this chart, it's really interesting to look at Malathion insecticide. It only persists for a day. But if you look at DDT, it can persist for 30 years in the soil. So it's just important to know the differences between some of these chemicals. And we can't just group them all into one category because some persist for a very, very long time. Environmental hazards are anything in our environment that can cause harm. So we've established that it's pollutants, human behaviors, draining wetlands, natural disasters like tornadoes. All of those are different kinds of environmental hazards. And scientists use a risk analysis of these hazards by instilling a 3-step process to analyze the risk. So they look at the risk. What is it? They characterize its toxicity or its dose and response to animals or humans. And then they determine how much exposure there would actually be. They then do what's called a risk acceptance. So they determine the acceptable level of the risk and balance that against the social, economic, and political considerations in the community where this is occurring. And then they manage it. They determine policy with input from private citizens, the industry, and interest groups. So when we want to compare different kinds of risk assessment, we want to look at qualitative versus quantitative. Qualitative versus quantitative. Quantitative is the numerical sum. So qualitative, when scientists look at this, they make a judgment of the relative risks of various decisions, and they determine the probability or the likelihood of an event occurring and the probability that that event will cause harm. With quantitative, it's a little bit of a different approach because they conduct a quantitative analysis. So they take the risk, and in order to determine the risk, they take the probability of being exposed to a hazard, and they multiply that times the probability of being harmed if exposed. So they have to do a lot of background research to determine this. What's really interesting when we look at probabilities of death in the United States, some of the factors that people perceive as having a high risk of death, like dying in an airplane crash, is really low compared to the factors that people presume are really low risk from dying of, like heart disease, which is actually the greatest risk if you look at it. Most people are not afraid of dying of heart disease, or they don't even think about it. But 1 in 5 people will die of heart disease. Cancer, 1 in 7. But if you look at an airplane accident, look at it, it's way down here. 1 in 5,051 deaths can be attributed to airplane accidents. So let's take a look. So it's all these preventable things like heart disease, cancer, stroke. Those are all preventable based on how we live our lives. Motor vehicle accidents are accidents, but risky behavior, risky driving could lead to more accidents. Falling, look at 1 in 218 people. Firearm assault, pedestrian accidents, drowning, fire or smoke, bicycling accidents, airplanes, hot weather, bee stings, lightning, earthquakes, and floods. So just interesting, the perceived analysis or perceived conception of what we decide we might die from, or most die from. So the outcome of a risk assessment of PCBs, polychlorinated biphenyls, by the EPA found that in the Hudson River, fish had unacceptable high concentrations of PCBs due to illegal dumping by General Electric. And so they had to put this sign up. So something to be aware of, that there's, companies will oftentimes just dump their illegal pollution into waterways because it's out of sight, out of mind. They don't see it, and they don't think that people are going to know. But what ends up happening is there could be a fish kill, and then there's going to be an investigation to find out what happened. So worldwide standards of risk fall under either the innocent until proven guilty principle or the precautionary principle. So the innocent until proven guilty principle says that if there's a potential hazard, it should not be considered until scientific data can definitively demonstrate that it causes harm. And then the precautionary principle is a little bit different. It says when there's a hazard that's plausible but not yet certain, we should reduce the actions and remove the hazard so that we can prevent any negative impacts. So, for example, the positive with precautionary principle is that there's fewer harmful chemicals that are released into the environment before we know what they can do. The negative is that beneficial chemicals could be delayed. So if we've got chemicals that really could be solving some problems and we use precautionary principle, we might not be able to solve a problem that might need solving in a timely fashion. A good example of this is asbestos. When it was first mined in the 1870s, it was mined until in the mid-60s in the United States. It causes a rare form of cancer called mesothelioma, and scientists linked this cancer to asbestos, but it took too many years for them to talk about it and to determine this, and many people died as a result. And this is just a graphic showing you the difference between innocent till proven guilty and the precautionary principle. It's much easier to go with the precautionary principle and save lives rather than just throw things out in the environment, because not only might it just initially kill people, but it could persist. And we've talked about the persistence of some chemicals. So the Stockholm Convention was a convention of 127 nations in 2001 in Stockholm, Sweden. And it was an agreement on restricting the global use of some chemicals, or POPs, persistent organic pollutants. 12 chemicals were banned and phased out or reduced. Some of them included DDT, PCBs, and certain chemicals that are byproducts of certain manufacturing processes. So the 27 nations of the European Union that made the agreement on how the chemicals should be regulated, that occurred in 2007, and they used the acronym REACH. And it stands for Registration, Evaluation, Authorization, and Restriction of Chemicals. So the United States, by the way, is not part of the European Union, so that is not something that we belong to. Something we probably should. And then at the end of the chapter, there's a case study on the global fight against malaria. Bill and Melinda Gates are they've created a foundation that supports the eradication of malaria. 350 to 500 million people every year are infected by malaria, and about 1 million people die. So the eradication in the US occurred around 1951, but it didn't occur in other countries because of the situations of poverty. Mosquito populations rebound quickly after spraying, so a neighboring country might not spray, and those mosquitoes don't care about the boundaries, right? And malaria, the pathogen, there's 3 different malarial pathogens, and some of them have evolved resistance to drugs. So eradication is very expensive. It's carried by the female Anopheles mosquito. So what Bill and Melinda Gates have done with their foundation is support anti-malarial medication and nets that are impregnated with pesticides to reduce deaths by 60%. Mosquitoes are typically out at dawn and dusk, and so if you can provide these nets that mosquitoes cannot get through that have pesticides in them, you can prevent the infections of malaria significantly. So look at that, 60%. That's it for chapter 16, guys.